In this video, we will explore the concept of distributed query processing. This involves executing database queries across multiple database sites or locations. Imagine a central query processor that needs to retrieve data from different databases spread across a network. These databases are labeled as Database Site 1, Database Site 2, and Database Site 3. The central query processor communicates with each of these sites to gather the necessary information to fulfill the query. Dashed lines with arrows indicate the communication pathways between the query processor and the individual database sites. Distributed query processing comes with its own set of challenges. Let's explore the main hurdles that need to be addressed in distributed query processing. The first challenge is data distribution and localization. Determining where the necessary data resides within the distributed system is a crucial task. Second, network communication overhead can be a significant bottleneck. The cost of transferring data between different sites must be minimized to achieve efficient query processing. Third, query optimization across sites is a complex undertaking. The query execution plan needs to consider the characteristics and capabilities of each individual site. Fourth, maintaining data consistency across all sites is essential. Ensuring that all data remains synchronized and accurate is critical for reliable query results. A central circle labeled Distributed Query Challenges is connected by lines to 4 smaller circles representing each of these challenges: data distribution, network overhead, query optimization, and data consistency. Now, let's examine the architecture of a distributed query processing system. The process begins with a client application that submits an SQL query. This query is then passed to a query parser, which transforms it into a parse tree, a structured representation of the query. Next, a global query optimizer takes the parse tree and generates an efficient execution plan that specifies how the query will be executed across the distributed sites. This execution plan is then handed off to the distributed execution engine, which coordinates the execution of the plan across the different database sites. Finally, the database sites perform local processing on the data according to the execution plan. There are arrows that point to the successive layers. First arrow is from the client application towards the query parser. Second arrow is from the query parser towards the global query optimizer. Third arrow is from the global query optimizer to distributed execution engine. There are 3 database sites that the distributed execution engine communicates to. Let's delve deeper into the query decomposition process. It consists of several steps. First, the global query is parsed into a syntax tree, which represents the structure of the query. Second, complex queries are broken down into simpler subqueries that can be executed independently. Third, the data location for each subquery is identified, determining which sites hold the relevant data. Fourth, the optimal execution sequence for the subqueries is determined to minimize data transfer and processing time. Fifth and finally, site-specific execution plans are generated, tailored to the capabilities and data distribution of each individual site. As an example, on the right side of the slide, the original global query is given and it is decomposed into subqueries. To ensure efficient query execution, several optimization strategies are employed. 2 prominent strategies are join order optimization and the semi-join strategy. Join order optimization determines the optimal sequence of join operations to minimize data transfer between sites. This reduces network overhead by joining smaller result sets first. Semi-join strategy involves projecting and transferring only the join attributes to filter irrelevant tuples before the actual join. This significantly reduces the amount of data transferred across the network. The original query is optimized using these strategies to come up with the optimized execution plan. Let's illustrate how the semi-join strategy works with an example. We will consider an original distributed join between 2 sites. Site 1 hosts the customers table, while Site 2 hosts the orders table. In the first step, the customer ID attribute is projected from the customers table at Site 1. In the second step, The projected values are used to filter the orders table at Site 2, selecting only the orders associated with the customer IDs received from Site 1. When it comes to distributed query execution, various approaches can be employed, each with its own trade-offs. Let's explore 3 common approaches. First, in the ship-whole relation approach, entire relations are transferred to a central site for processing. This approach is simple but inefficient for large datasets. Second, in the ship matching tuples approach, filters are applied at the source sites and only matching tuples are transferred. Third, in the query shipping approach, query operations are sent to the data sites rather than moving data. All 3 approaches are represented in the slide as different processes happening across different sites. Distributed transaction management presents unique challenges compared to single-site transaction management. These challenges include maintaining ACID properties, that is, atomicity, consistency, isolation, and durability, handling partial failures, implementing distributed concurrency control, ensuring global serializability of transactions, and managing distributed deadlocks. An example of distributed transaction is given where 2 update statements are being executed on 2 different sites within a transaction. In summary, distributed query processing involves decomposing complex queries, optimizing execution across sites, and managing transactions to maintain data consistency. Strategies like semi-joins and query shipping help reduce network overhead. The success depends on balancing data locality, network bandwidth, and processing capabilities of distributed sites. Looking ahead, several trends are shaping the future of distributed query processing. These include edge computing integration, artificial intelligence-driven query optimization, real-time distributed analytics, and privacy-preserving query processing. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.